Hi, my name is Chris and I welcome you to our second DOCKTITE video. In the first video I showed you how to install DOCKTITE. We created this button here with the 4 submenus, each for every covalent docking step of DOCKTITE. And today I will show you DOCKTITE in action. We will do a pose prediction study for this complex here. In this complex, a ligand with benzoxyzinone warhead is bound to a pancreatic allostase. Benzoxyzinone warheads react in a ring opening reaction with the nucleophilic residue of the receptor, and this ring opening reaction implies that the unbound state, the geometry of the unbound state is very different to the bound geometry, and this makes it hard for a variety of docking programs to predict this pose. But I show you how accurate and easy DOCKTITE will do this for you. We open the PDB ID directly from MOE. I just type the PDB code. I clicked here on RCSB PDB and then the PDB code and on OK. MOE will open the complex fully automatically, and the first step is to prepare the receptor. We have to assign charges, we have to assign protons. I use the Ember12 EHT force field. In most cases this force field is very sufficient. It's parameterized for proteins as well as for small molecules by extended Hickel theory. And I will use this in all DOCKTITE tutorials. To prepare receptor, MOE gives you a very comfortable way to do this just by clicking on LigX. This opens a graphical user interface with a variety of structure preparation steps. We will leave all as default, but we will unclick the refinement step. On OK. And now MOE is preparing our receptor. We protonate. We optimize the system. We delete waters that are far away from the active site. And we have not much to do manually here. Now the preparation is finished. We hide nonpolar hydrogens just for a better view, and we save the prepared structure as 1INC prep MOE. Now, as you have read in the manual, DOCKTITE needs several receptor files. The first receptor file is without a ligand and with the nucleophilic atom. It's this oxygen here. We have the serine residue. I can mark it by making it a little bit thicker. And now you see here's the nucleophilic atom. It's the oxygen of the hydroxyl group of the serine residue. And this atom has to be named Cap. We can do this by just going here into the name field, type in Cap and press return. Now we named this atom Cap. And this receptor file with the nucleophilic atom named Cap and the deleted ligand is named COFRAC prep MOE. This is the default, but of course you can assign an own name, that's no problem. But when you use the default, then it is pre-typed in every graphical user interface of the DOCKTITE workflow. Okay, this is the first file. The second file is with the ligand in place. And the nucleophilic residue and the neighboring atoms deleted. For this purpose, we go to the sequence editor and we look for the purple serine here. The purple margin indicates that this one is covalently bound to a ligand. We select the surrounding amino acids and we show the selected. Now we click on one of the atoms of the nucleophilic residue with clicking on Control. So we select the whole residue and we delete it. We delete also this amine group and this carbonyl group. We can do this by holding Shift and clicking on the 3 atoms of the amine group and the 3 atoms of the carbonyl group, and we press delete. So we have now a structure with ligand in place, with no nucleophilic residue, and with the surrounding atoms, the directly surrounding atoms, deleted. We save this structure, for example, as 1-INC serine deleted .mo. Okay, these are the receptor files we need, and now we need a ligand database. For this purpose, we open a new database. We name this database ligands.mdb. And now we have to sketch our molecule in the pre-reacted form. Of course, you can also get it from the PDB, but in post-prediction, it's better to not get it from the PDB, as there are informations stored in the ligand because it comes from the PDB. It has the position of the original structure, and this is not the right way to do it. Just give no information of the real pose before you make the post prediction. So we write it, so we sketch it in ChemDraw, for example, and we just copy it into MOE with Control C and Control V. Now you see this is flat, and we will just make short energy minimization. We check that this is as configured here. Yes, we have a constraint assigned. It's blue. So this is our ligand in the pre-reacted state. We can get this in the ligands database by clicking on Edit, New, Entry. MOE asks for ignoring visibility, selection. So this is the only molecule in our MOE system. We can ignore all this. And we have now our pre-reacted ligand in the database. Now we can start with DOCKTITE. The first step is the warhead screening step. Now we have just one ligand in our database, so it is not a real screening. It's more a warhead reaction step. But when you make a virtual screening, for example, that then you have many ligands, some of them are not covalent ligands, and then it's a real screening. DOCKTITE will recognize a predefined warhead, will react, will tag, and this is done all fully automatically. So now we start with step 1, the warhead screening. The graphical user interface appears. Our input file is ligands.mdb that we made just before. The warhead reactions file is warhead filter, as we have no bivalent ligand here. And the output file should be named tagged out. We are finished. You see here the input molecule. You see the output molecule that has reacted with the nucleophilic atom. And as you know from the menu, we use a tantal as tagging atom for the nucleophilic residue. This will guide as a tag in the second step for building the chimeric nucleophilic residue ligand atom molecule. You can see here which rule was used. In this case, the benzoxycenone 2-tantalum. The second step is using the receptor and isolating the nucleophilic residue and attach its side chain to the ligand. And this step is called side chain attachment. We use our receptor file, COFRAC-PrEP-MO, where the nucleophilic atom is named Cap and no ligand is present. The input file for the ligands is the tagged out file that we prepared just before, and the output file has to be named attached ligands. We also create a pharmacophore file. I show you how this pharmacophore file looks like in a few moments. The attachment is finished. And now we see the nucleophilic residue shown here. This is the serine residue, is attached to the electrophilic atom of the ligand from the benzoxycenone warhead. We have also a stereo field. When we have prochiral warheads, then at least 2 stereoisomers are generated, and the configuration of the warhead atom, in this case this would be this one, would be assigned here. So it could be R configured, S configured. When it's in a double bond, it could be E configured or Z configured. And this is shown in the stereo field. When we have an achiral warhead atom that is not in a double bond, then we see an X. Let's open this chimeric molecule in the MOE window. And additionally, the generated pharmacophore file. You see, in this pharmacophore file we have very narrow features for every heavy atom of the nucleophilic residue. These have the atom number of the respective atom. And we have an atom Q feature. The atom Q feature is generated from informations of the pocket, and it helps to guide the ligand into the pocket. In this case we have a very small ligand, so the automatic atom Q feature will be sufficient, but sometimes it helps when you generate such an atom Q feature by yourself. I will show you how to do this in one of the next videos. We use the SiteFinder application and create an atom queue feature on a dummy atom that we created with the SiteFinder. I will show you this in the next video. Okay, now we come to the final docking step. For this docking step, we use just the dock graphical user interface of MOE, and we open our 1INC ZER-DEL MOE receptor file. Because we will dock in this one, the nucleophilic residue is now part of the ligand, so we had to delete it. And because of sterical reasons, we also have to delete the neighboring atoms. This is no problem, because there's never an interaction between backbone atoms of the nucleophilic residue and the ligand. The name of the output file should be dockmdb. You can use the default. The site could be the ligand atoms. We can check. Yeah, this is right. This is the site we want to use. We want to use the automatic DOCKTITE pharmacophore file. And as ligands, we want to use the attached ligands MDB that we created. We want to rotate bonds, as we want MOE to generate conformations for us. Optionally, we can create conformation database before, but in this case we can use just the automatic conformation generator. Now this is really important. If you don't use pharmacophore placement, you will not get any results, because in this case, where the pharmacophore placement is used, we align all the generated conformations to this pharmacophore file while the docking, while the placement. When we use triangle matcher, we have no information about the pharmacophore while the docking, and we filter it afterwards so that our ligand atoms, our chimeric molecules, fit in this pharmacophore model is very unlikely, and the result is an empty output database. So you have to choose as placement method pharmacophore. We raise the number of return poses to 5000, and we use the affinity DG scoring function. We retain 100 poses, use a force field refinement with also affinity DG scoring function, and we retain also 100 poses. Now the next step is also very important. You have to click on Configure and set a very high force constant of 1 to the power of 9. Because this force holds the nucleophilic residue at the position of the pharmacophore features that we use for the docking step. Otherwise, the ligand will come out of the pharmacophore file and it will be filtered afterwards, and you have also no output. So this is really important to get sufficient results of DOCKTITE. Now we click on Run. We can open the SVL window and have a look what MOE is doing now. MOE performs a pharmacophore search with the alignment of the chimeric molecule into our prepared pharmacophore model. And when it has found sufficient conformations, then they will be scored and the top 100 will be refined. Now we have 7,101 hits. We keep 5,000 of them, we score them, and the top 100 is refined now. You can see the nucleophilic residue is held in place very strict because of the narrow pharmacophore features. You can also delete the pharmacophore feature for the nucleophilic atom. Then you allow a rotation through this bond here, and this will give you more degrees of freedom while the docking step. Sometimes this is a very good idea when you don't know exactly the rotameric state of the nucleophilic side chain. Okay, as this refinement will last approximately 30 minutes, I have prepared this file for you, and we cancel the job and use the prepared one. I prepared it exactly the same way for the further steps. Click on cancel, dock. We close the window. Now I delete the dock.mdb and rename dock.prepared.mdb into it. The output file looks like this. We have 41 poses generated, and the scores and the energies that MOE calculated for each of this pose and the refinement step. As rescoring is much more accurate with the cleaved ligand, where the side chain is deleted from the ligand, we have a step 4 that is named side chain cleavage. It's fully automatic. We use the docking output file as input, and we name the output file cleaved. Now you see on this position was the side chain before, and this is now deleted. Now we want to calculate RMSD values for our generated poses. For this purpose we use the template from the PDB structure. We just delete everything else but the ligand. We can do this by holding Control and clicking off one atom of the ligand. That will select the whole ligand. Then we go on Select, Invert. Now we select anything else than the ligand, and we click on Delete. Now we have just the ligand, and the RMSD values will be calculated from the position of the heavy atoms of this template. This small RMSD SVL file can be downloaded from the SVL Exchange website, and it's a very nice tool to calculate RMSDs for a whole database. The reference should be all atoms from the MOE window, and the placements are from the cleaved MDB. And we want also to write it in cleaved MDB. Now we have a new field with RMSD values, and we sort them ascending to the RMSD value. You can see from this RMSD value that DOCKTITE is able to very precisely generate conformations that fit or that match the original crystal structure. To show you this in the complex, I will make the original ligand green and we browse through our database with the new ligand shown in red. As you see, the predicted pose was predicted very accurate. Also the second one and the third one. What I didn't show you now is how to predict this scores or the best fitting pose when you don't have the RMSD value calculated. This is done by a rescoring with the knowledge-based scoring function DSX, and I will show you this in the next video. And there you will see that this knowledge-based scoring function is able to identify the near native pose very accurate and more precise than the scoring functions implemented in MOE in this time. I hope this little tutorial helped you, and we see us again in our next video. Thank you very much.